Welcome to the Deep Dive. We sift through complex research, pull out the core insights, and, well, hand them straight to you.
Glad to be here.
Today, we're tackling maybe the biggest puzzle in physics, trying to finally bring together quantum mechanics and gravity.
The grand unification quest, yeah. It's been the horizon goal for, what, a century?
Exactly. And for most of that time, it felt purely theoretical. You'd hear about it in the context of black holes, or maybe the Big Bang's first tiny fractions of a second. Stuff we couldn't really touch or test.
Absolutely. Always seems like physics happening at energy scales or curvatures we just couldn't replicate.
But here's the twist, and it's what our sources are digging into today. That quest. It's actually moved. It's landed right on the laboratory bench.
That's a big claim. How so?
Well, it's thanks to decades of really groundbreaking work, step-by-step progress in what are called macroscopic quantum systems. Things we can build and measure.
Okay, macroscopic quantum systems. We should probably unpack that right away.
Definitely. And our mission today is to connect the dots. How does the incredible precision people achieved in, say, superconducting electrical circuits work? That's definitely Nobel-level stuff. How did that platform let us test a really specific and, frankly, pretty radical theory called QUV?
QUV, Quantum Universe Vacuum-Modified Gravity, right?
Yeah. And the headline, the big reveal here, is that the claim is we can now use quantum entanglement, the spooky connection between particles happening inside a circuit, to see if it literally curves space-time around it.
Okay, that's the hook. Moving from abstract math about black holes to potentially measuring space-time curvature from entanglement in a lab. That's quite a leap.
It really is. And it hinges on those two pillars you mentioned. So maybe let's start with the foundation, the experimental side.
Sounds good. Let's define the key concepts first. So number one, macroscopic quantum systems. What are we talking about? In essence, these are engineered systems where you get billions, literally billions of particles like electrons moving in a metal wire to stop acting like a chaotic crowd and instead behave as one single coordinated quantum object.
Like a single giant atom almost.
In a way, yeah. You see quantum effects we normally associate with tiny things like quantum tunneling or having discrete specific energy levels, but you see them happening on a scale large enough to, well, observe directly with lab equipment. Think of it as the ultrasensitive eyes. We need to potentially see these tiny gravity effects.
Okay, so that's the platform. What about the theory it's supposed to test? QUV.
Right, QUV theory. This is the framework making the predictions. Its core idea is pretty paradigm shifting. It says gravity isn't fundamental in the same way as, say, electromagnetism.
Not a basic force.
Exactly. Instead, QUV proposes that gravity, the curvature of space-time, emerges from something deeper, specifically from the structure of quantum entanglement and the way information flows within the quantum vacuum. And they formalize this mathematically with something called the entanglement tensor, which gets written as Qμ. That's the piece that supposedly modifies Einstein's equations.
Qμ. Got it. So the experimental systems provide the eyes, and QUV provides the specific, potentially visible target.
That's the connection we're exploring today, how one enables the search for the other.
All right, let's really dive into that experimental side first, the macroscopic quantum foundation. Because getting quantum mechanics to show up on a large scale, that sounds incredibly difficult. Almost impossible, right?
Oh, it is. Normally, quantum effects are ridiculously fragile. Any little interaction with the outside world, a stray vibration, a tiny bit of heat can destroy the delicate quantum coherence. It's a process called decoherence.
Things just snap back to behaving classically like everyday objects.
Exactly. The bigger something is, the faster this usually happens. So the standard intuition was always quantum for the small, classical for the big.
But this foundational work, the stuff by people like John Clark, Michel Devoret, John Martinis, the context for this whole experimental platform they showed, that's not always true.
Precisely. They demonstrated, through painstaking experiments over years, that in certain special materials, superconductors are the prime example, but also things like specific Fermi liquids. You can maintain quantum coherence across distances you can practically see. Millimeters, even centimeters sometimes.
How does that even work? How do you get billions of electrons to cooperate like that?
It comes down to the collective behavior in these materials. In a superconductor, for instance, electrons form pairs, Cooper pairs, and these pairs behave like bosons, which are particles that like to be in the same quantum state.
Unlike electrons normally, which are fermions and have to stay separate.
Right. So these Cooper pairs can condense into a single shared quantum state. Think of it like Billions of tiny ripples on a pond suddenly merging into one single giant, perfectly synchronized wave that stretches across the whole pond. That unified wave is the macroscopic quantum state.
You used an analogy earlier about a stadium.
Ah, yes. Imagine a stadium packed with people, all milling about randomly. Then suddenly, a conductor gives a signal, and everyone instantly stands up and starts marching perfectly in step, absolutely synchronized. That collective, unified rhythm, that's the quantum phase coherence across the whole system.
And this collective state, this marching in step, is what they call a Bose condensate. I hear that term a lot.
That's the technical term, yes. It signifies that a significant fraction of the particles, the Cooper pairs, in this case, have all fallen into the lowest possible energy state together. It's crucial to note the number of particles actually in the condensate might be different from the total number of electrons in the chunk of metal.
Okay, so not all of them are in sync, but enough are.
Enough are in that single coherent state to dominate the system's behavior and give it these global quantum properties. It's this shared rhythm, this macroscopic coherence, that's the key to making the whole thing work as a quantum device.
So we have this amazing state of matter, but how do you actually use it? How do you measure things with it, especially these potentially tiny gravitational signals?
That's where the real technological ingenuity comes in, specifically with the Josephson junction. This is the workhorse device in these experiments.
Okay, Josephson junction, what is it?
It's surprisingly simple in concept. You take two pieces of superconductor and you separate them with a very, very thin layer of insulating material, like an oxide. Just a few atoms thick sometimes.
So thin that quantum effects can cross it.
Exactly. The Cooper pairs, those electron pairs acting as a single quantum entity, can tunnel right through that insulating barrier. It's like they don't even see it, almost. This happens without needing to apply any voltage, which is bizarre from a classical perspective.
Quantum tunneling, but on a large-scale circuit component.
Precisely. And because the current flowing across this junction is exquisitely sensitive to the quantum phase difference between the two superconductors, the junction acts like an incredibly sensitive detector. It lets you listen in on the dynamics of that Bose condensate, that collective quantum state.
These are the eyes you mentioned earlier.
These are the eyes, and the absolute cornerstone experiment that proved these systems were genuinely quantum on a large scale was observing macroscopic quantum tunneling, MQT.
MQT. What did that look like in an experiment?
Imagine the quantum state of the circuit is like a ball sitting in a valley. Classically, it needs enough energy to roll over the hill next to the valley, but in MQT, you see the entire system, this collective state of billions of particles, spontaneously tunnel through the energy barrier, appearing on the other side, even though it didn't have enough energy classically to make it over.
Whoa! The whole system just poofs through the barrier.
In a probabilistic sense, yes. Observing these discrete tunneling events, measuring their rates, confirming they follow quantum rules, that was the crucial validation. It proved that the system's dynamics are quantized, meaning it has specific energy levels, like an atom, not a continuous range like a classical object.
And why is that finding, MQT, so critical for trying to test quantum gravity theories like QUV?
Because it demonstrates unequivocally that you have maintained quantum coherence in a system large enough and controllable enough to potentially interact with or be sensitive to extremely subtle effects. If MQT works, it means your circuit truly is a macroscopic quantum object.
It's sensitive enough to maybe feel these tiny geometric fluctuations QUV predicts.
That's the hope. MQT proves the platform has the necessary quantum coherence and the measurement sensitivity. It allows us to confidently measure things like the precise energy spectrum, the epsilon of P you might see in papers, within this complex many-body system. Without the MQT results underpinning it all, suggesting we could use these circuits to hunt for quantum gravity signals would just be, well, pure speculation.
Okay, so the stage is set. We have these incredibly sensitive quantum circuits, validated by Nobel context work like MQT. Now, let's bring in the theory they're trying to test. QUV, entanglement, geometry, and the Qμ tensor.
Right. Now we look at the target.
So QUV's big idea. Gravity emerges from entanglement.
Yeah.
How does that link actually work? What's the mechanism? The sources talk about the entanglement Hamiltonian. That sounds intense.
It is a central concept. If you want to say entanglement creates geometry, you need a mathematical operator, a Hamiltonian, that turns one into the other. The entanglement Hamiltonian is proposed as exactly that operator.
Is it just an analogy, or is it mathematically rigorous?
The claim is it's rigorous. It builds on some pretty deep results from quantum field theory in curved spacetime. There's this known connection between observers, geometry, and temperature.
You mean like the Unruh effect, that weird idea where if you accelerate through empty space, it feels hot?
Precisely that. The Unruh effect predicts that an accelerating observer perceives the vacuum not as empty, but as a thermal bath with a specific temperature, the Unruh temperature, which is directly proportional to their acceleration.
Okay. How does that connect to entanglement and gravity in QUV?
QUV takes this connection and elevates it. It essentially defines a temperature operator, let's call it T sub x, linked to this entanglement Hamiltonian. The crucial step is that the theory mathematically relates this temperature operator directly to the curvature of spacetime. Specifically, the acceleration of sub x that determines the Unruh temperature is derived from the Ricci curvature tensor, the thing that measures spacetime curvature in general relativity.
Wait, so acceleration causes perceived heat, and acceleration is related to curvature via gravity. So QUV is saying spacetime curvature is fundamentally a kind of temperature, an entanglement temperature.
But that's the core assertion. The mathematics essentially says 6Tx pofar H's, where that acceleration exiscil comes directly from the curvature axis. So high curvature means high entanglement temperature.
Okay, my mind is slightly blown. Curvature is temperature.
It's a profound shift in perspective. And here's where it gets really interesting, building this self-sustaining picture. QUV proposes a feedback loop.
A loop? How?
High spacetime curvature creates a high effective Unruh temperature, T sub x. This high temperature then actively modulates the amount or structure of quantum entanglement in the vacuum. But then, and this is the key emergent step, that very entanglement structure feeds back and generates the spacetime geometry itself.
Whoa, so curvature heats the vacuum, which changes entanglement, which creates the curvature, it builds itself.
That's the proposed mechanism. Spacetime geometry isn't a static background. It's a dynamic, self-organizing structure emerging from this interplay between curvature, temperature, and entanglement. It suggests the smooth classical world Einstein described emerges from a much weirder, discrete, quantum information-based reality underneath.
Like the pixels on a screen resolving into a smooth image when you step back.
That's a decent analogy. And the mathematical framework relies on ideas like random geometric graphs to show how this discrete, quantum pixelated structure can indeed smooth out and converge to the continuous spacetime we experience at larger scales.
Okay, this is a completely different way of thinking about gravity. And this new physics, this entanglement-driven source of gravity, is what's captured in that Qμ tensor you mentioned.
Exactly. Qμ is the mathematical object that represents this extra quantum information-based source of stress energy. It's the term QUV adds to the right-hand side of Einstein's field equations, the famous Gₘₙ plus Tμ plus adding a quantum gravity term directly into Einstein's equations. And this Qμ isn't just one thing. The sources say it's tripartite, breaks into 3 parts.
That's right. The tensor naturally decomposes into 3 components, each with a distinct physical meaning. It's actually quite elegant.
Okay, let's break them down. What's the first part? The first is the alpha term. This one directly represents that curvature-temperature coupling we just discussed. Mathematically, it looks like alpha Rₘ RT2 involving the Ricci tensor Rₘ and the temperature T. But the really striking thing here is the coupling constant, alpha itself.
Alpha. What's special about it?
It's enormous. The theory calculates its value to be roughly $1.72 times 10 Kelvin squared in standard SI units.
10 to the 67th power. That's astronomical.
Yeah.
Why so big? What does that signify?
It tells a crucial story about why gravity seems so weak in our everyday experience compared to forces like electromagnetism. Because alpha is so huge, it means the underlying quantum entanglement effects, which are happening at the microscopic Planck scale, need this massive amplification factor just to produce the relatively gentle space-time curvature we observe macroscopically.
Ah, I see. So gravity isn't inherently weak. It's that the quantum engine driving it needs this giant gear ratio, this huge alpha, to make its effects felt on our scale. It bridges the gap between the quantum world and the cosmic scale.
Exactly. It reframes weakness as a consequence of emergence from a much finer-grained reality. Okay, so that's alpha.
What's the second part? The beta term.
Yes, the beta term. This one is fascinating because it connects gravity directly to information theory. It's written as beta Qôbie nablomi as polono. The key parts here are the coupling constant beta, Boltzmann's constant K sub b, and crucially, Nabla-S, the gradient of entanglement entropy.
Gradient of entropy, like how spread out the entanglement is.
Precisely. This term says that if entanglement isn't uniformly distributed, if there's a gradient, a change in entanglement entropy from one place to another, that gradient itself acts as a source of gravity. It modifies the classical heat equation, implying that the flow of quantum information is inherently tied to space-time geometry.
So it's not just energy density, like in the normal Qμ curving spacetime, but the flow or unevenness of information itself.
That's the radical idea here. Information gradients have geometric consequences. It puts thermodynamics and information theory right at the heart of gravity.
Okay, alpha for curvature temperature, beta for information gradients. What's the third part? Gamma.
The gamma term. This one, written as gamma, Qμ, represents the most fundamental underlying quantum structure of the vacuum itself. Think of Qμ as representing a kind of fluctuating field associated with the basic quantum bits, or qubit spinors, that QUV postulates make up spacetime at the lowest level.
Like the pixels in the analogy earlier, their inherent jitter.
Kind of, yeah. It's the residual quantum texture of spacetime that survives even after smoothing out to the large-scale continuum. This term predicts a kind of fundamental, subtle geometric noise inherent in the vacuum.
Wow. Okay, so you combine alpha, beta, and gamma. That gives you Qμ. And adding that to Einstein's equations is what turns QUV from a cool idea into something you could actually go looking for in a lab.
Exactly. It provides concrete mathematical predictions. And that brings us back full circle to those macroscopic quantum systems. They are potentially sensitive enough to actually detect the effects of these individual alpha, beta, or gamma terms.
This is the perfect bridge. We have the supersensitive quantum circuits, the eyes from the Nobel context work, and we have these three specific predicted quantum gravity effects from the Qμ tensor, the targets. So let's get into the nitty-gritty, the experimental blueprint. How exactly do you use these circuits to look for signals from alpha, beta, and gamma? Let's start with gamma. How do you test for that underlying quantum vacuum structure, the Qμ field?
Right. Test 1 is about detecting the geometric fluctuation field, Qμ. This leverages the extreme sensitivity of those Josephson junctions we talked about.
The ones that allow macroscopic quantum tunneling.
The very same. The gamma term, Qμ, predicts that this fundamental Qμ field representing the vacuum's qubit structure isn't just theoretical. It should manifest as a real physical fluctuation in our spacetime.
A fluctuation of what? Like a jiggle in spacetime.
Essentially, yes, a very subtle, low-frequency geometric noise. And because Josephson junctions are incredibly sensitive to tiny electromagnetic changes, which would be influenced by these geometric fluctuations, the prediction is that this Qμ field should create a measurable, anomalous voltage noise across the junction.
Noise. But wouldn't the junction already have noise? From heat? From electronics? How do you tell this geometric noise apart?
That's the critical experimental challenge. Standard thermal noise, Johnson noise, shot noise, they all have well-understood characteristics, usually broadband spectra determined by temperature and resistance. The predicted Qμ noise, however, should be different.
How so?
It's expected to be non-thermal, meaning its strength doesn't just depend on temperature in the usual way. And importantly, it should have a specific spectral signature, likely concentrated at lower frequencies, reflecting the proposed discrete, perhaps fractal scattering structure of the vacuum itself. It wouldn't fit the standard fluctuation dissipation theorem that connects noise to temperature and resistance.
So you're looking for a specific kind of static in the junction's voltage, a kind that doesn't look like heat.
Exactly. A structured, low-frequency, non-thermal voltage flicker that you can't explain away with conventional physics. Detecting that specific signature would be incredibly powerful evidence, direct evidence, arguably that these underlying quantum vacuum fluctuations, the gamma term, are real and actively influencing geometry.
And this is only feasible now because the MQT experiments pushed the sensitivity floor down so low, they learned how to isolate these junctions from normal noise well enough.
Precisely. The meticulous work done to observe MQT shielding, filtering ultra-low temperatures created the exact conditions needed to potentially hear this incredibly faint geometric whisper above the thermal roar. It's searching for a very specific needle in a very well-characterized haystack.
Okay, that's test 1. Listen for the vacuum's geometric hum via the gamma term. What's test 2? The sources mentioned something about fractal circuit geometry. That sounds wild.
It is pretty wild. This test stems directly from a core postulate of QUV, that space-time at its most fundamental level isn't a smooth continuum, but has a fractal dimension.
Fractal, like those patterns that repeat themselves when you zoom in. Sierpinski triangles and things.
Exactly like that.
Wow.
The idea is that spacetime has a self-similar structure. QUV connects this to quantum information, proposing that the mutual information shared between two regions of the vacuum stays constant under specific scaling transformations, like zooming in or out by a fixed factor, say, 10. This mathematical property is characteristic of fractal geometries.
Okay, space-time might be fractal. How on earth do you test that with a circuit?
You try to build the fractal into the circuit and see if it changes its quantum behavior in a predictable way. Specifically, the proposal is to fabricate Josephson junctions, where that thin, insulating barrier isn't just a flat, simple layer, but is patterned with a precise fractal design.
Like etching a tiny Cook snowflake onto the barrier.
Something like that, yes. Using advanced nanofabrication techniques, the kind refined for building complex quantum chips, again, building on that Nobel context work, you'd create junctions with specific fractal geometries.
And what are you measuring then? What should change?
You measure the junction's critical current. That's the maximum amount of supercurrent it can handle before the superconductivity breaks down and it develops resistance.
Okay, measure the current limit, and QUV predicts.
QUV makes a remarkably specific prediction. It calculates that a Josephson junction built with a particular fractal pattern, reflecting the proposed fractal dimension of spacetime, should exhibit a critical current that is exactly or approximately 23% higher than an identical junction made with a standard, flat Euclidean geometry barrier.
23%. That's specific. Not just higher, but 23%.
Yes. That number comes directly out of the theory's calculations based on the assumed fractal dimension. It's a hard, quantitative prediction. If you build this fractal junction and measure its critical current, it should be measurably, significantly higher by that specific amount, purely because its geometry resonates, in a sense, with the underlying fractal structure of spacetime itself.
That's astonishing if true. You change the shape of a component on a chip, make it fractal, and its fundamental quantum electrical properties change by a fixed percentage predicted by a theory of quantum gravity.
It would be a profound confirmation. It links macroscopic engineering, the shape you etch, directly to the deepest proposed structure of reality. And again, it relies on the ability to both fabricate these intricate nanoscale structures and make ultra-precise quantum measurements, capabilities honed in the pursuit of macroscopic quantum phenomena.
Mind-boggling. Okay, test 1 targets gamma via noise. Test 2 targets the fractal nature via critical currents. What about the beta term, the one about information gradients? How do you test entropic gravity and information flow?
This brings us to test 3. It goes back to that beta term, beta kb dou times the entropy gradient squared terms. Remember, this term predicts that gradients in entanglement entropy, Nabla-S, should act like a source of gravity, modifying thermodynamics.
Right, information imbalance having weight.
So the test aims to create and measure the effects of such an information gradient in a controlled setting. The macroscopic quantum circuit platform is perfect for this. Why? Because the quantum state of these circuits, especially near phase transitions, can often be described using models from statistical physics, like the tilted washboard potential.
Washboard potential, what's that?
It's a useful analogy. Imagine the energy landscape of the quantum circuit's state variable, like the phase difference across a junction, looks like a corrugated washboard tilted slightly downhill. The state is like a particle sitting in one of the valleys. Quantum tunneling, MQT, is the particle sneaking through the ridge to the next valley. External biases, like currents, tilt the washboard more or less.
Okay, so it's a model for the energy states and transitions. How does it help test the beta term?
Because you can manipulate the system near a critical point, like where the particle is just about to spill out of its valley, a phase transition. These critical points are known to be extremely sensitive to subtle influences. The idea is to engineer a situation where you create a gradient in entanglement entropy across the circuit without necessarily changing the total energy significantly.
How would you create an entropy gradient?
Perhaps by differentially coupling different parts of the circuit to external reservoirs, or using quantum control techniques to prepare specific entangled states in one region versus another. The details would be complex, but the goal is to create a controlled imbalance in quantum information.
And if the beta term is real, what should happen? What's the measurable signal?
The prediction is that this engineered entropy gradient, this Nabla-S, should produce a measurable physical effect not accounted for by standard thermodynamics or electromagnetism. This could manifest as an anomalous force, perhaps a tiny mechanical push on part of the circuit, or as unexpected heating or cooling effects, a modification to heat transport.
So you're looking for heat flowing unexpectedly, or a tiny push just because the information is arranged unevenly.
Exactly. It would be evidence that the gradient of entanglement entropy itself is acting as a source term in the effective gravitational field experienced by the system. It would directly test the idea that gravity has an entropic informational origin, validating the physics behind the beta term. It's about seeing if information itself exerts a force or influences energy flow in a way that standard physics doesn't predict.
Okay, these three tests, the noise, the fractal current boost, the entropic force, they're incredibly specific, grounded in the QUV theory and enabled by the MQS platform. If, and that's a big if, but if these tabletop experiments start yielding positive results, confirming these Qμ effects, what does that mean for the bigger picture? Does it just stay in the lab?
Oh, absolutely not. The implications would be profound, extending immediately to cosmology. Right now, cosmology has some significant puzzles that standard physics is struggling with.
You mean things like dark matter and dark energy?
Those are the big ones, yes, but there are also tensions within the standard model itself. The most prominent one currently is the Hubble tension.
Right, the disagreement about how fast the universe is expanding right now.
Exactly. Measurements of the expansion rate, h0, based on the very early universe, like the cosmic microwave background data from the Planck satellite, consistently give a lower value than measurements based on the local present-day universe, using things like supernovae or surveys like DSI.
And the error bars don't overlap. It seems like a genuine discrepancy.
It really does. And it strongly suggests that our standard cosmological model, known as lambda CDM, lambda-cold dark matter, is missing something. It works incredibly well overall, but this tension points to a crack in the foundation.
So how could QUV, a theory tested in tiny circuits, possibly resolve a cosmic scale problem like the Hubble tension?
Through a really elegant mechanism built into the theory. The idea that the strength of that entanglement geometry coupling, primarily governed by the alpha term, isn't constant. It should be scale dependent.
Meaning gravity works slightly differently on different distance scales.
Effectively, yes, driven by the underlying quantum information physics. QUV introduces a scale-dependent coupling, let's call it alpha of k, where k represents the spatial scale or wave number. This scale dependence arises naturally from the concept of entanglement saturation.
Entanglement saturation, what does that mean?
Think of it like a sponge. A region of the quantum vacuum can only hold so much entanglement, just like a sponge can only hold so much water. There's a maximum limit related to the holographic principle and black hole entropy bounds, like the Bekenstein bound.
Okay, so the vacuum can get full of entanglement. How does that affect the Hubble constant?
It provides a natural way to reconcile the different measurements. At small scales within the universe, the high K regime probed by early universe measurements like the CMB, the entanglement in the vacuum has had plenty of time and opportunity to reach its maximum capacity. It's saturated.
The sponge is full.
Right. And when entanglement is saturated, the QUV theory predicts that the modification to gravity, the Qμ term, gets suppressed. The theory naturally reduces back towards standard general relativity, or lambda CDM. This preserves the successful fit of the standard model to the early universe data, which points to the lower value of h0.
Okay, so it matches the early universe measurements. But what about the measurements today in the local universe?
That's the key. At large cosmological scales, the low K regime probed by local measurements like DSI, looking at galaxies nearby the universe, is effectively younger or less dense in terms of entanglement generation over those vast distances. The entanglement hasn't had time or room to fully saturate.
The sponge isn't full yet on those huge scales.
Exactly. In this unsaturated regime, the QUV modification, the Qμ term driven by LFAC, is not suppressed, it's active. And the theory is tuned such that this active modification provides just the right amount of extra push or altered gravitational dynamics to explain the higher value of h0 observed locally.
Wow. So it naturally produces two different effective expansion rates depending on the scale you're looking at, purely based on whether the underlying quantum entanglement has maxed out or not.
That's the proposal. And crucially, it's not just an arbitrary fix. The scale dependence arises directly from the fundamental postulate about entanglement saturation. It offers a physically motivated resolution to the Hubble tension, linking quantum information limits to cosmic expansion. It gives QUV significant explanatory power if borne out.
That connects the lab bench to the cosmos in a really direct way. And it leads to this even broader perspective you mentioned earlier, the information universe.
It really does. If these ideas hold up, it suggests a radical rethinking of reality. It points towards a view where the fundamental constituents aren't particles or fields in the traditional sense, but perhaps bits of quantum information.
The universe as a giant quantum computer.
That's one way to think about it, yeah. Frameworks like QUV, along with related ideas like causal set theory, which posits spacetime is built from discrete events where the fundamental rule is simply order plus number equals geometry. They all converge on this notion. Gravity, entanglement, quantum rules themselves might just be emergent properties of how information organizes and flows through this underlying discrete, possibly fractal network.
Geometry arising from relationships between information bits.
Exactly. And there are even hints in the source material suggesting that the very reason we experience three spatial dimensions might not be arbitrary.
Oh, why three?
The theory suggests that 3 dimensions could be a kind of geometric sweet spot, an optimal configuration that allows the vacuum to maximize its energy density, making structure formation possible, while remaining stable. It might be the most efficient way for the universe to structure itself for complexity and, potentially, computation.
So 3D space isn't just a given, it's potentially an optimized information processing architecture.
It's a fascinating possibility. It merges fundamental physics with concepts from information theory and even theoretical computer science. It suggests that studying gravity might ultimately become synonymous with studying the principles of quantum information processing on a cosmological scale. Concepts like the Leverrier-Ricci curvature, which measures distances in evolving information networks, become relevant tools for understanding physical geometry.
Okay, let's try to synthesize this. We've journeyed quite a distance here. We started with the nuts and bolts of superconducting circuits, the Josephson junctions, the Bose condensates, the validated phenomenon of macroscopic quantum tunneling. That's the legacy of the Nobel context work. It built the incredibly sensitive platform.
The eyes, yeah. The tool sharp enough to potentially see these effects.
Then we explored QUV theory, this radical idea that space-time geometry emerges from quantum entanglement, formalized in the Qμ tensor. That gave us specific targets to look for.
Targets broken down into those 3 terms. Alpha linking curvature and temperature, beta linking geometry to information gradients, and gamma representing the fundamental vacuum fluctuations.
And crucially, we outlined 3 concrete, potentially falsifiable experiments using the MQS platform to hunt for signals from those terms. Test 1. Listening for that specific, non-thermal geometric noise from the gamma term's sigma-mu field in Josephson junctions.
Right, the vacuum's hum.
Test 2. Building fractal patterns into junctions and looking for that predicted 23% boost in critical current, testing the fractal spacetime idea.
The geometric enhancement.
And test 3. Using washboard potentials near critical points to see if engineered entropy gradients information imbalances from the beta term create measurable forces or anomalous heat flows.
Testing if information itself has weight.
If any of these experiments yield positive results, the implications ripple outwards, potentially resolving cosmic puzzles like the Hubble tension through scale-dependent gravity based on entanglement saturation. It points towards a universe fundamentally built on information.
It really does set the stage for a potential paradigm shift. And if these superconducting systems do start confirming this link between entanglement and geometry, if we detect these Qμ effects, well, the next step seems almost obvious, doesn't it?
What's that? Building bigger circuits?
More than that, we need to turn to the one technology we're developing that is explicitly designed to create, control, and manipulate complex entanglement patterns: the quantum computer.
Ah. So use quantum computers not just to simulate physics, but to be the experiment.
Exactly. They could transition from being tools for calculation to becoming actual functioning quantum gravity laboratories.
Yeah.
We could potentially use qubits not just to model spacetime, but to generate tiny, measurable perturbations in geometry through controlled entanglement.
That's a fascinating and slightly scary thought.
It is, and it leaves us, and you the listener, with a really profound question to consider. If space-time, the very fabric of reality, truly does emerge from organized patterns of quantum information, what does that imply about the ultimate nature of reality itself? Could it be that the universe, at its deepest level, is a form of computation? What are the limits to complexity in such a system?
So the next time you look around the room or gaze at the horizon,
You might try seeing it not just as empty space, but as a dynamic, incredibly complex, self-organizing information system, a substrate that is constantly computing the geometry we experience. It definitely changes your perspective.